This is section 9.7. I never did check. Did we do 9.6? Yeah. Okay. So 9.7, Taylor Polynomials and Approximations. Okay, goal of this section is to show how polynomial functions can be used as approximations for other elementary functions. Define a polynomial function P that approximates another behavior F, begin by choosing a number C, and then go through all that. Okay. So this first part, we're approximating this graph right here with this linear form. Looks like a tangent line, doesn't it? And it's not a very good approximation, as you can probably see. But the idea is to take something that's maybe a little bit hard to work with and come up with something easier to approximate. Now here's our steps for finding a first degree polynomial approximation at an x value or a point. Step 1, label the x value as a, and if necessary, plug a into the function to find the y value, which we will then label as b. Step 2, find the derivative. Step 3, plug in a into the derivative from step 2 and simplify. Label it as c. And then plug a, b, and c into y equals b plus c times x minus a and simplify. Get that linear approximation, that line. But it's specifically at a x value or a point, not the entire graph. And I believe, it's been a while, I believe where that's all headed is you then use these in differential equations, if I remember. Okay, so let's take a look at number 9. So f of x is equal square root of x over 4. And they're giving us c is equal to 4. They're basically giving us the x value. That's what that represents. And the instructions say, find a first degree polynomial p sub 1 whose value and slope agree with the value and slope of f at x equals c, and then use a graphing utility to graph them, which, like you say, should look like the tangent line. Okay, so step 1, label the x value as a. So a is 4. If necessary, plug a into the function to find the y value. We're not given the y, we're just given the x here. So we're going to plug 4 into our function. Is it really 4? What's that? That is. So we're going to have the square root of 4 over 4. It gives us 2/4 or 1/2. And then it says label that as b. So b is equal to 1/2. Step 2, find the derivative. Well, this I can rewrite as f of x is equal to 1/4 x to the 1/2 power. Take your power, put it out in front, lower it by 1. Four times 2 is 8, and take the x to negative 1/2 back down below and becomes x to the positive 1/2. Which gives us 1/8 square root of x. Step 3, plug in a into the derivative from step 2. So we're going to plug this 4 in. So f prime of 4 is going to equal to 1/8 square root of 4. Square root of 4 is 2. So that gives us 1/16. And it says to label that as C. So we got our A, got our B now, we got our C. Step 4 says plug A, B, and C into y equals B plus C times x minus A. So I'm going to have y is equal to 1/2 plus C, which is 1/16, x minus A, and A is 4. Now, nothing really exciting about what we're doing here. This right here is just our initial point, isn't it? When we go through and find derivative and we plug in that x value, we're finding the derivative, the slope, at that point. And which is our slope is m. So this, if I took the 1/2 over here, is y minus y1 equals m times x minus x1. So that's just the point slope form. Now, we'll simplify that. That gives us 1/16 x, multiply those together, minus 4/16. 4/16 is 1/4, so I got 1/2 minus 1/4. So we got 1/16 x. And let's say negative 1/4, and this would be 2/4, so that gives me a positive 1/4. If I were to graph that, y is equal to square root of x over 4. And y is equal to 16th x plus 1/4. And what are we looking at? Point 4 1/2. Which looks like right here. And you can see we've got our straight line there. And yeah, it does correspond with our tangent line, doesn't it? So Got one more of those. F of x is equal to secant x. C is equal to pi over 6. Same instructions. Okay, step 1, label the x value as A. This is the x value they're giving us, so that's A. And if necessary, plug A into the function to find the y value, which we'll label as B. So I'm going to find f of pi over 6. That gives us secant pi over 6. Now secant is related to cosine. Cosine is x, right? So secant is 1 over x. So 1 over square root of 3 over 2. Flip it, multiply it times the top. We get 2 over square root of 3. Multiply top and bottom by square root of 3, and we get 2 square root of 3 over 3. To find the y value. Secant pi over 6. And we'll label that as B. So B is equal to 2 square root of 3 over 3. Okay, so we got 2 of the items. Step 2, find derivative. Derivative of secant is secant tangent. Step 3, plug in A from into the derivative from step 2. So A was pi over 6. So f prime of pi over 6 is equal to secant pi over 6 tangent pi over 6. Now secant, we just found that was 2 square root of 3 over 3. Sometimes I get too excited and start putting it in the right form when it would have been easier to just leave it the way it was. But we'll see how this one works out. The other part I need is tangent pi over 6. Tangent is y over x. So I'm going to have 1/2 over square root of 3 over 2. So 1/2 over square root of 3 over 2. Those 2's cancel. So I got 2 square root of 3 over 3 times 1 over square root of 3. Square root of 3's cancel, and I'm left with 2/3. And that'll be C. So, step 4. Plug A, B, and C into this formula. So y is equal to B plus C times x minus A. B. B was 2 square root of 3 over 3. Plus C. C is 2/3. Times x minus A. And A was pi over 6. So we got 2 square root of 3 over 3. Multiply the 2/3 through, and I got 2/3 x minus 2 pi over 18. Multiply top and bottom by 3 here, and I get, yeah, I guess I'll multiply by 3. We get 6 square root of 3 over 3 plus 2/3 x minus, that simplifies to pi, let's try it again, 6 square root of 3 over 9. With top and bottom here, divide by 2, so that gives us pi over 9. So I'm going to have y is equal to 2/3 x plus, these have the same denominator, so I'll put them together. I got 6 square root of 3 minus pi over 9. And that'd be our answer. Questions on that first technique? Now the next part, let me come over here to talk about it. Talks about Taylor and Maclurin polynomials. And we got the e to the x, and we can find a polynomial approximation of it. So again, we're trying to take something that's maybe not that easy to work with and change it to just x minus something to a power with coefficients. Doesn't really say why, but if I remember right, again, it's a differential equations where you see it. Now, definitions of that. Definitions of the nth Taylor polynomial and nth Maclaurin polynomial. If f has n derivatives at c, then the polynomial p sub n of x equals f of c plus f prime of c times x minus c plus f double prime of c over 2 factorial times x minus c squared plus dot 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 plus our f to the nth derivative of c over n factorial times x minus c to the nth power is called the nth Taylor polynomial for f at c. If c is equal to 0, then I won't say it, but that's our formula we use, and that's called the nth Maclaurin polynomial for f.
That's supposed to make it simpler?
Sort of. But yeah, it's kind of debatable. Back in the dark ages, when they came up with all this, there was no calculator and so forth, and to calculate e wasn't very easy. But if you could do like squared, third power, especially a polynomial, it doesn't get any easier in a polynomial. But you're right, with the tools we have now, it doesn't make as much sense. And they give you some pictures here. What happens when you start taking more and more polynomials? The Taylor polynomials: p sub 0, p sub 1, p sub 2, p sub 3, p sub 4. If you look at this piece right here, P sub 1 is this line right here. Of course, the P sub 1 means you got a linear, right? And it's not a very good approximation of that. You go another power, P sub 2, it becomes quadratic, doesn't it? So, and you see it's okay, it's a little bit better. You get to P sub 3, which is cubic. Remember, that's your graph goes out like that. And a little bit better. And then you get the P to the 4th, and you see it's perfect along that piece right there, right? Now, it's not perfect everywhere. That's not the goal. There's a certain limitations where you can use it. And that's why they got it centered around a value, not just anywhere. Okay. It's pretty easy, but it's tedious. And I think I've only picked one that might be a little bit challenging. But they didn't put real challenging ones in there. The idea isn't for you to spend an hour and a half on one problem.
Spend an hour and a half on one.
Yeah, you could. Yeah, that's why they try to keep them pretty simple. Because the idea is you take the derivative over and over. Yeah, when you do the quotient, maybe 8 times. Yeah. If you look at the, there was one that I wasn't sure. I couldn't look at and I couldn't see all the derivatives, but maybe it comes out nice. Either way, I wasn't going to show it.
Would this be on the test?
Not a hard one. I'm going to show number 21 because that's the product rule, and that'd be doing the product rule 4 times. This would be 1 minus x to the negative 1 power, and if I took the derivative over and over, that'd be easy. The secant is the only one I wasn't sure about because the derivative of secant tangent, right? And which then becomes a product rule, and but notice what they have here. N is equal to 2. So you don't have to go very far on it. Now, if you change that to n equals 8, which gives you a better approximation. The more of these you do, the better your approximation is. Yeah, that'd be horrible then. So you'll notice all these are pretty easy. 32, but n equals 2. So, yeah, they've deliberately picked problems easy to work, which is good. Okay. So the instructions here says find the nth Maclaurin polynomial for the function. The Maclaurin is easier. It's this second formula right here. Now, it's telling us that n is 4. So we want to find, you can plug 4 in for the n here. We want to find p sub 4 of x. So that's our goal. P4. Yeah. Now, if you look at this formula, it goes up to the nth derivative. Since n is 4, we're going to need 4 derivatives, won't we? So, first derivative of e to the power is e to the power times the derivative of the power, so that'd be 4e to the 4x. Second derivative, again, e to the power is just e to the power times derivative of the power, so that gives us 16e to the 4x. Third derivative, and this is type that you can see on a test. I'm not going to put something real horrible on there. Of course, I guess it depends on your definition. 64e to the 4x. And the fourth derivative, 256 e to the 4x. No, now comes you notice on all of these, we're plugging 0 in, aren't we? Always. So it doesn't say C, it doesn't have it always says 0. So right beside it, f prime of 0 would be 4e to the 4 times 0. 4 times 0 is 0, e to the 0 is 1, times 4 is 4. F double prime of 0, 16e to the 4 times 0, which is 16. And our third derivative will be 64e to the 4 times 0, which is 64. And our fourth derivative, 0, 256e to the 4 times 0, which gives us 256. Okay, so now we're ready to plug it into our formula here. Again, where the n is, I'm putting in 4. So p sub 4 of x is equal to, and then I got f of 0. I didn't find f of 0, did I? If I plug 0 in my original function, I'm going to have e to the 4 times 0, which gives me 1. So I'm going to have 1 here, plus f prime of 0. F prime of 0 is 4 times x plus f double prime of 0. F double prime of 0 is 16 over 2 factorial, x squared. Plus, let me see where it's going. This will be my third derivative. So I'm plug in 256 over, and notice what it's increasing by. 2 factorial, 3 factorial, 4 factorial, increasing by 1, isn't it? So this will be 3 factorial. And this will be x to the third. What? 3 factorial? Oh, up on top. Jeez, you're right. My eyes got off. Plus 256 over 4 factorial, x to the fourth. So we got 1 plus 4x plus 2 factorial, 1 times 2, 16 divided by 2 is 8. So we got 8x squared. 3 factorial is 1 times 2 times 3, which is 6. 64 over 6 gives us 32 over 3. X to the third. 4 factorial, 1 times 2 times 3 times 4. So I'm going to take my 24. So 256 over 24, x to the fourth. So we got 1 plus 4x plus 8x squared plus 32 over 3, x to the third. That simplifies 128 over 12, 64 over 6, 32 over 3. And that would be our polynomial approximated right around that x value, specifically x equals 0. Um, 2 factorial is 1 times 2 3 factorial was 1 times 2 times 3, which is 6. Then the 4 factorial was 1 times 2 times 3 times 4, which gives us 24. And that's how you simplify those. So our original was f of x equals e to the 4x. Y equals e to the 4x. Maybe. There it goes. And the approximation down there is y is equal to 1 plus 4x plus 8x squared plus 32 over 3 x to the third plus 32 over 3 x to the fourth. Again, where we're looking is right around the x equals 0, because that's what Maclaurin is focused on. And when you look at that, does it look pretty dead on? It does, doesn't it? So that's an excellent approximation at that point. Well, it's pretty good, long ways up, isn't it? Of course, your definition of pretty good might be. If I had to zoom out to even see them separate. Okay, let's skip ahead. And we're going to take a look at number 39. Number 39 says approximate the function at the given value of x using the polynomial found in the indicated exercise. So if you go home, work problems out of the book, pay attention to this set of problems right here because they go hand in hand with the ones we just looked at. Okay, so we just came up with this. Try to figure out what we're going to do. We're going to take that x value, the 1/4, and plug it into our function. So it's 1 plus 4 times 1/4 plus 8 times 1/4 squared plus 32 over 3 times 1/4 to the third plus 32 over 3 1/4 to the fourth. I might be able to do some of this. It's force cancel, it gives me 1. That's 1/16 times 8 is 8/16 or 1/2. 32 over 3 times 1 over 4 to the third. 4 times 4 is 16, times another 4 is 64, I think. That's 32 over 3. 4 times 4 is 16, times another 4 is our 64, times another 4 is 256. One plus 1 is 2, plus 1/2 gives us 5/2. This 32 cancels that. That gives us 2 there. That gives us 1/6. I don't know why I'm doing this. 16 over 128. So 16 thirds times 1 over 128. If I multiply top and bottom by 3 here, that gives me 16/6. 3, 15, 16, 6 plus 8/3 times 1 over 64. I guess that's 1 over 24. Yeah. Multiply the top and bottom, that's 65 over 24. Maybe. 65 over 24?
I got 59.
You're probably right.
Just plug the entire thing in, enter the fraction.
You see why their math department talked about they're not going to require people to buy a T or 3, 10, or 4. Because there's so many online resources for it. You're going to find that doing it on the calculator is much easier. 1 plus 1 plus 1/2 plus 32 divided by 3. 1 divided by 4 carried 3 plus 32 divided by 3. 1 divided by 4 carried 4. Assuming I typed it in right. That's not right. What did I screw up? 112. Okay, let's try it again. That looks better. Okay. I don't even know what that is. Math. No, it's mine. 65 over 24. But let's see if that's right. If I were to plug in the value here, my x that I'm plugging in is 1/4. If I plug in the 4 here for the x, 4 times 1/4 is 1. So let's see what e to the first power gives us. See how that's an approximation? They don't really ask you to do that, but that's the whole goal of what you're doing right here, is you find approximation at that point. Well, where is it centered around? It's centered around 0, isn't it? If we put 0 in, well, let's see what we get. I guess I ought to just put my polynomial in. You get it that time? Okay, so 1 plus 4x plus 8x squared plus 32 divided by 3, x to the third. By the way, they do have problems where they just want you to build tables like this of values, but I'm not going to show you those problems. I don't want you to worry about them because it's quite tedious. Not hard. Okay, assuming I put it in there correctly. This next one here would be e to the 4x. Okay, so let's go to our table now. Okay, put in our 1/4. Get that. And that's what we already saw. But it really is centered around 0. And if I put 0 in, they both come out perfect, don't they? If I chose something a little closer to 0, 0.01. Pretty good, right? If I chose something a little further away from 0, like 2. What does that say? Geez. It goes haywire pretty fast there, doesn't it? Interesting. So anyway, main thing I want to point there is when you do an approximation, the approximation is only good for a little bit. And I'm not going to have you work any of the problems, but I'll show you the formula where it figures, how, the error and so forth around it. Okay, back to here. This is another one I figured I could take the derivative over and over pretty easy. F of x is equal to sine x, n equals 5, which means we're going to need to find the fifth derivative. Now, it's the Maclaurin series, or Maclaurin polynomial, I should say. And again, for the Maclaurin polynomial, you plug 0 in for each one of these. So I'll do that as I go along. Sine is 0. So I'm here at 0. Sine is our y. So what's that equal to? 0. Now our derivative. Derivative of sine is cosine. And I guess I might as well go ahead and just do all the derivatives real fast. Derivative of cosine is negative sine. Derivative of negative sine is negative cosine. Our fourth derivative, the derivative of cosine by itself is negative sine with the negative out in front, flips it to a positive sign. And derivative of sine is cosine. Remember our unit circle here at 0. This is the point 1, 0. So f prime of 0 would be cosine of 0, and cosine of 0 is 1. F double prime of 0 would be negative sine of 0, and sine of 0 is 0, so negative 0 would be 0. Our third derivative, we'd have put 0 in here, and cosine of 0 is 1, and I have a negative on front, so that's negative 1. Our fourth derivative, we got sine of 0, which is back to 0, and our fifth derivative of 0, we have cosine of 0, which is 1. And we're finding p sub 5 of x. I'll go ahead and write down the formula just so you see everything is. F of 0 plus f prime of 0x plus f double prime of 0 over 2 factorial x squared plus our third derivative over 3 factorial x to the third, fourth derivative 4 factorial x to the fourth, and fifth over 5 factorial x to the fifth. So that's our formula. F of 0 is 0 plus f prime of 0 is 1 times x. F double is 0, or 2 factorial x squared. The third is negative 1 over 3 factorial x to the third. The fourth is 0. 0 over 4 factorial x to the fourth. And the fifth is 1. 5 factorial x to the fifth. That 0 drops away. 1 times x is x. 0 drops away, minus 3 factorial is 1 times 2 times 3, which is 6. So that's minus 1 6 x to the third. That drops away because it's 0 on top. Plus 5 factorial, I think it's 120, but I'm probably wrong. 20, 60, 100, okay. 1 over 120 x to the fifth. And again, we don't necessarily think a sign is that difficult, but back in the way back then when they didn't have calculators with this little button that said sin and cause on it, it wasn't so easy. They had to use tables, and that was maybe even they did something before they had tables. Didn't they do some of that? No, they did logs with the slide rule, didn't they? But in very primitive ways. So the approximation gave them something a lot more tangible they could work with. Questions on it? Let's see, what was that? Okay, let's take a look at this one. This one looked a little interesting, though, when I looked on Calc Chat, so I wanted to make something sure I wouldn't show you something that would take me 45 minutes to do in class. The derivative seems to come out nice for some reason. F of x is equal to x, e to the x, and n is equal to 4. And we're still in the Maclaurin polynomial, so that's an easy one. Yeah. So then we need to find 4 derivatives because our n is 4. Product rule, this is P, this is Q. So I got x e to the x plus e to the x. For our second derivative, the derivative of x e to the x is just this. So we're going to have x e to the x plus e to the x. And then the derivative of e to the x is e to the x. So that gives us x e to the x plus 2 e to the x. I see why it comes out nice. Because no matter what, you always have this x e to the x here, right? Which goes back to the derivative of that, or the derivative is this. So I got x e to the x plus e to the x. The derivative of 2e to the x is 2e to the x. I think I even see the pattern on this. Maybe. So it's 3e to the x. And then our fourth one, we'll have x e to the x plus e to the x. The derivative of 3e to the x is 3e to the x. And that gives us 4e to the x. Besides the tediousness of it, would it be that hard to even take this to the 15th? No, because it looks like
3x e to the x plus 15 e to the x.
yeah. So it's you wouldn't even have to write them out because now that you see the pattern. And probably it's even become nicer when we plug 0 in, because like you pointed out, this first term will always drop away. The what?
We're only left with the number.
Only left with the number. Yeah. So f of 0, 0. They actually got names for some of these. I don't know if this one has a name, but if I plug 0 in here, I got e to the 0, which is 1. My second, if I plug 0 in, I've got 2 times e to the 0. E to the 0 is 1. That's 2. This will be 3. This one will be 4. And is that my last one? That's my last one. Okay. That actually came out super, super nice. Okay, so from our Maclaurin polynomial, p sub 4 of x is going to equal to, and there is a pattern here. It's not like the first two are different, even though it looks like it. That's f of 0 over what? N factorial, n minus 1, 3 factorial, 2 factorial, 1 factorial, 0 factorial. There's no x here, but this would be x to the 0. Then the next one is our first derivative over 1 factorial, x the first, plus our second derivative. I almost think it'd be easier to remember if they didn't put the first two terms as different. I don't know what that was. There we go. Okay, so f of 0. Remember we said we'll start at 0, so that's 0. 0 over 0 factorial times x to the 0 plus, this one came as 1. 1 over 1 factorial x plus, this was 2 over 2 factorial x squared plus 3 over 3 factorial x to the third plus 4 over 4 factorial x to the fourth. First part drops away. 1 factorial is 1. 1 over 1 is 1 times x is x. 2 factorial is 1 times 2, which is 2. 2 divided by 2 is 1. That's x squared. 3 factorial is 1 times 2 times 3. Basically, 3 drops cancels with that. And I'm 1/2. X to the third. 4 factorial. 1 times 2 times 3 times 4. The 4's cancel. And I'm left with a 6 on the bottom. So it gives me plus 1, 6, x to the fourth. Now the next two change. They're based upon find the nth Taylor polynomial for the function centered at C. So now we're no longer restricted to just focusing around 0. Here we can plug any number in here and find the approximation around it. So this one's a little bit harder. Not harder, it's more tedious, I should say. Okay, number 27. f of x is equal to 2 over x n is 3, and c, which is our x value, is 1. Now let's look at what our formulas want. To find a p sub n for that polynomial, we have to find the nth derivative. So since our n is 3, it means we have to go up to third derivative. Now this is 2x to the negative 1, if I take that up on top. So for our first derivative, take your power, put it out in front, lower your power by 1, or negative 2 over x squared. For our next derivative, take your power, put it on front, negative 2 times negative 2 is 4, lower your power by 1, or 4 over x to the third. For our third derivative, which is where we can stop, take your power, put it on front, so negative 3 times 4 is negative 12, lower your power by 1, or negative 12 over x to the fourth. Now you see here, it's now telling us to plug c in to our function and to our derivatives. So c was 1. So f of 1 is going to equal 2 over 1, or 2. F prime, our first derivative, we're going to have negative 2 over 1 squared, or negative 2. For the second derivative, we're going to have 4 over 1 to the third, which is 4. And for our third, we're going to have negative 12 over 1 to the fourth, which is negative 12. Now our formula is this first one here, so I'll replace the n with 3. So p sub 3 of x is equal to f of c, and c was 1, so I got f of 1 plus f prime of 1 times x minus c, so x minus 1, plus, and we got our second derivative, over 2 factorial times x minus c, or x minus 1 squared, and our third derivative over 3 factorial times x minus 1 to the third. Well, f of 1 we said was 2. F prime is negative 2, or first derivative is negative 2, x minus 1. Second derivative was 4 over 2 factorial. 1 times 2 is 2, x minus 1 squared. Third derivative was negative 12 over 3 factorial. 1 times 2 times 3, and x minus 1 to the third. That's 4 divided by 2 is 2, x minus 1 squared. 2 times 3 is 6, negative 12 divided by 6 is negative 2, x minus 1 to the third. Now there's no need, because Well, if you plug in a value, it's easier in this form, I think, if you're doing it by hand. So can I plug in x equals 15 there? I could, but would it be meaningful? Yeah,
Would not be perfect.
because this is centered around c is equal to 1.
So it's better to do
1, 1.1, 1.2. So yeah, centered around 1 is where this is really going to be the best. Now that's not saying 15 won't come out perfect also. I don't know. I'd have to graph them, look at them, evaluate them. But remember that one we did and it went from 1 to 2 and it went pretty radical on the difference? Yeah. So.
It looks good on the graph, but it's really zoomed in.
Yeah. I never even thought about that because the X scale was so close together that even though I was going way up, it looked like, boy, this is right on. If you actually went out to 2 and expanded that X scale, you would have saw they were pretty far off.
Might be hard to graph on the calculator.
Yeah. Okay, one more of those. F of x is equal to square root of x. Well, this is an easy one. Only second derivative is all I have to go. And center around 4. Okay, so we know that we're going to need the second derivative because the n controls how many derivatives we're going to have. So our first derivative, keep in mind this is x to 1/2. So our first, take your power, put it up in front, lower it by 1. Or that's 1 over 2 square root of x. The x to negative 1/2 goes to the denominator, becomes x to the positive 1/2, which is square root of x. For our second, take your power, put it on front. 1/2 times negative 1/2 is negative 1/4. Lower your power by 1, so it becomes negative 3/2. Or negative 1 over 4. And that's x to the 3/2, which is x to 1/2 to the third power. Or negative 1 over 4 square root of x to the third power. I put it in that form because we're going to plug in c is equal to 4. And square root of 4 is easy, isn't it? 4 to the 3/2 power is not so easy, although it's not hard. Okay, so our formula says, for the Taylor polynomial, it now says we're going to plug c in. So c is 4. So f of 4 is equal to square root of 4, which is 2. We'll plug in 4 to the first derivative. That's going to be 1 over 2 square root of 4. That's 1 over square root of 4 is 2 times 2 gives us 1/4. And for our second derivative, we'll plug 4 in. I'll have negative 1 over 4 times the square root of 4 to the third power. Square root of 4 is 2. 2 to the third is 8. Times 4 is 32. So we've got negative 1 over 32. Okay, so piece of our formula says we need f of c C is 4, so we got f of 4, plus f prime of c, so f prime of 4 times x minus c, so x minus 4 to the first power, plus f double prime of 4 over 2 factorial, x minus c, or x minus 4 squared. Well, f of 4 is 2, plus 1/4 times x minus 4, plus negative 1 over 32. 2 factorial is 1 times 2, x minus 4 squared. Two plus 1/4 times x minus 4, plus 1 times 2 is 2, and then multiply it times the 32. We got negative 1 over 64. X minus 4 squared. Now again, the bigger you're in, the better the approximation is. 2 n equals 2 is probably not greatest, is it? Might be good enough for what we're doing here. This is really something I don't think you probably do in engineering. Do you have to take like a numerical methods class where you program math like this? But if you're going into mathematics, you would. I programmed this way back when. I took a class, and very confusing class. He gave us his programs that he wrote, and we were to modify it. I'm not sure if I got much out of that class. But my programming skills were very minimal at that point, too. So. Okay. Last note here. Taylor's theorem. See, if a function f is differentiable through order n plus 1 and interval I contains c, then for each x and I there exists z between x and c such that, this is all true, where r sub n of x is equal to f to the n plus 1 derivative of z over n plus 1 factorial times x minus c to the n plus 1 power. And this down here gives you one useful consequence of this is that it gives you this piece right down here, and r is your remainder. So r refers to your remainder. Let me see if I got that in the book. It's a different kind of remainder, but right idea. Because if it was perfect, then f of x would equal to our polynomial, wouldn't it? So here, the remainder refers to like how much it's off. Does that make sense? So when we talk of r sub n in this formula, the r sub n is referring to our error. And I'm not going to have you do it, but you'd plug in your values, plug in your c, plug in your x, if you have one, your n, and then you find the derivative, and then you take the maximum. Remember that from Calc 1, where you take a derivative, you set it equal to 0, you solve it, those are your critical values, you build your test cases, you do your increasing, decreasing, you find your max, so forth. It's a lot of work to just find a remainder. But you go through that, and then you have the absolute value of the remainder is less than or equal to a number. And this number, you remember with the absolute value, that's like you have the negative version of it and the positive version on this side, and the remainder is somewhere in the middle. So let's see if they got an example. Not quite the one I wanted, but they're leaving a lot of steps out, but they go through and find the fourth derivative. They find the maximum of that. They plug it into the values here. Now, interestingly enough, they don't put a negative version of that over on this side. They just put 0. Because really, what's my error going to be? In a political poll, you say you're going to be 3% off, right? Did they ever tell you you're going to be a negative 3% off? No, that really confused people, wouldn't it? So actually, that's why they started at 0 there. Okay. That's the end of 9.7. So let's go ahead and take a 5-minute break, and then we'll go into part of 9.8, if not all.